Hey guys, Miss Lake here. I am going to take a second to review with you simplifying radicals. This should not be a new idea. You did cover simplifying radicals in Algebra 1, and we are really going to be using it during this unit. So we wanted to take a second and just kind of review. So hopefully after you see a few examples, you'll be like, oh yes, I remember this. And if you don't, guys, you are going to have to get help from your teacher because, like I said, you will be using this entire unit over right triangles. So, okay, so in order to be able to simplify radicals, first it's important to be aware of what the perfect squares are. So I would review and memorize these. Again, mostly you're going to need, the most common ones are really the 1 through 12. Every once in a while you'll see 15 and 20 and sometimes 25. So that's why I kind of just included those, but I did also kind of include everything up to 20 and 25. But really, like I said, 1 through 12 are the most common ones that you see, and then 15, 20, and 25. So I would really try to kind of memorize those. Okay, so some rules for simplifying radicals is that the product property of square root. So if I have two things underneath, the product of two things underneath the square root, I can split them up into the product of each of those roots. Similarly, if I have something divided or a quotient underneath a square root, I can split that up into the square root of one over the square root of the other. So sometimes we really will go kind of back and forth between these, kind of whichever one helps you. Okay, so because of these rules, we're able to simplify radicals. And then remember, you also can never, like here and here, we wouldn't be able to leave that radical in the denominator, okay? So you can never leave a radical in the denominator that is not considered simplified. So what you have to do is called rationalizing the denominator. I'm going to be doing those in examples. It's actually example 6 and 7. So you'll be able to get a little review about how we do that. Okay, so I am going to show you two different methods for simplifying radicals, and then I'm going to kind of, do a little bit of each and down in the examples. And guys, you just need to know how to do both. You don't really need to know how to do both of them. You really need to pick which one you like and use that one, okay? So I'm going to give you two methods. One may be more familiar to you than another, but like I said, it is really, really up to you as to which one your preferred method is. Okay, so the first one is called the factor tree. Okay, so what that is that we are breaking up the number underneath the radical into just a tree of factors. Okay, so if it's even, I usually start out by trying to divide it by 2, and you can go below your factor tree or you can go out to the side. I'm going to go out to the side because I don't have as much room below. So I know that this is even, so it divides by 2, and that's 2 times 56. Okay, so 2 is prime, so I'm going to split up 56. So 56, that is 2 and 28. Okay, again, here I see I could either keep dividing by 2, or I know that 28 is also, I could break it down by 4 and 7, and then that 4 would break down into a pair of 2's. Okay, so let me go back up here for just a second and say, remember that when we have the square root of a squared, right? The square root of something squared, it just comes out as the thing, right? Because the square root and the square, those are called inverse operations of each other. They undo each other. So when I have a square root of something squared, that just cancels out the square and I just get the number. Okay? Now, whenever we're doing the factor tree method, what we look for once we have it factored is we're looking for pairs, because a pair is like a 2 squared. This is a 2 squared. Right here is a 2 squared. And then I see what I have. I call this one a loner, right? So these are buddied up. So we always say kind of this is sort of what we call the buddy method. Sometimes you'll hear it called that, is that when something has a buddy, it gets to come out. And then if it doesn't have a buddy, it stays in. We call him a loner, right? So when I sit there and I say, okay, this is really 2 squared, so one of these comes out and one of those comes out, because the square root of 2 squared is just 2. So I'd get a 2 on the outside here. I'd have another 2. And remember, when things come out, they multiply with things that are on the outside. And so there came my buddies, and then I have my loner. He's going to stay inside. So I just have that 7 by itself. So I combine these terms by multiplying them, and I get 4 root 7. Okay, now let me show you another method. So another method that you can use is dividing by the perfect square. So basically you're looking for kind of the largest perfect square that is a factor. So what we usually do is we take this number, and so then what you're going to use is, this is kind of where you're going to use these perfect squares. So what I'm going to do is I am going to take this number, 112, and I'm going to just start dividing by the perfect squares. And usually I start with 10 squared or 100. So I'm going to divide it by 100. Well, I know that's not really going to go even. So I'm going to divide 112 by the next smallest perfect square, right? So I'm kind of just going through this list of perfect squares. So I look and I say, okay, 112, I did it by 100. Now let's do it by 81. No, 112 divided by, what's the next one? Would be 64. So I'll divide by 64. No, 112 divided by 49. No, 112 divided by 36. No, 112 divided by 25. No, 112 divided by 16. Hey, there we go. There's a factor. Those are 2 factors, and one of which is a perfect square. So what that tells me is that this square root of 112 could also be written as the square root of 16 times 7. Okay, well, we know what the square root of 16. That's a perfect square. So the square root of 16 is 4. So the 4 comes out, and then the 7 stays in. So guys, check it out. You get the same answer. So it really is, do you like to kind of break it down so you can see it all together? Or is it easier for you to just kind of guess and check with that list of factors and find the pair that works? Really, either one will be fine. Okay, let's look at a few more examples. All right, so I'm going to kind of go back and forth between the methods. Again, what I typically would do is when it's a smaller number like 75, or I can kind of automatically recognize what some of the factors are, then I usually will do my factor tree. Like here, I know that 75 is 3/4, right? Or 3 times 25. So it's sort of like I'm kind of doing both of these, right? Because I knew 25, a perfect square, was a factor. And then I see that 25 breaks down to my 5 and a 5. So I have a pair of 5s. I have a loner 3. So the thing that's circled, one of those gets to come out, and then the 3 stays inside. Okay, now 891. Now I'm not going to lie, this is one of those ones where I'm like, I have no idea what the factors of 891 are. So I am going to start, and I am just going to start dividing it, okay? Again, I will usually start with like the factors around, 100 or so and work my way down. I might miss a larger factor, but usually that's going to hit it. So I'm going to clear that out, and I'm going to say, okay, 891. First, I'm going to divide by 100. I know it's not going to go in evenly, right? That didn't work. So 891, then we divide by 81. Hey, look, that works. So I know that 891 can be written as the square root of 81 times 11. We know that the square root of 81 is 9, so this can simplify to 9 root 11. Okay, square root of 216. Again, I can't right off the bat I know it's even, so I could break it down by evens, but I'm going to go ahead and do the factor trick, or the dividing by the perfect squares. So I'm going to take 216, and again, I know it's not going to divide by 100, so maybe we'll start with 81 this time. No, 216 divided by 64, no. 216 divided by 49, no. 216, I know it's not gonna, let's see, 36. Hey, there it is. Okay, 216 is 36 and 6. So I could write this as the square root of 36 times 6. Okay, we know that the square root of 36 is a perfect square, so that would be 6 root 6. Okay, now, whenever we are multiplying with radicals, you multiply the things on the outside by the things on the outside, and the things on the inside by the things on the inside. But when we're simplifying radicals and I have to multiply things on the inside, I usually don't actually multiply them together. I'm going to write this as I'm going to put the two numbers on the outside, the 3 times the 2, and then instead of multiplying these two together and getting some gigantic number, I'm going to just leave them apart because I'm going to break them down anyway. So I look and I say, okay, let's do my factor tree. So 24, that's 4 and 6. 4 breaks down to 2 and 2. There's a pair of 2's. Now I know 6 breaks down to 2 and 3. Right now I don't think that that's going to help me, but let's kind of keep looking. So over here I have 5 and 9. I see 9 breaks down to 3 and 3. So what I have a 5, and then I'd have a 2 and a 3, and none of those would actually have, would match up. So I have a loner 6 and a loner 5. Okay, so now these 2's and 3's, they are going to come out and multiply with the 3 and the 2 that's already there. So I'm going to kind of show myself I've got the 3 times the 2 that was already there. Then I'm bringing out another 2 and another 3. So times 2 times 3. And then I'm going to multiply those back together. So 6 times 5. So 3 times 2 is 6, times 2 is 12, times 3 is 36, times the square root of 30. Okay, so now we get into these ones where there's a radical in the denominator. Now remember, like I said up there, radicals, we cannot leave radicals in the denominator. So we either want to see if the fraction, if it can simplify, or if we can, then if it doesn't simplify, then we will have to do what's called rationalizing the denominator. Now, when I see things like this and I say, oh, that could be reduced, I'm going to go ahead and try to reduce this. Now, remember, this is the same as if I write it all under the radical. And I know that 200 divided by 8, that simplifies to the square root of 25, and we know the square root of 25 is just 5. So it's much easier. You want to see first if they can simplify or you can reduce the fractions, because sometimes that's going to make it easier than actually having to rationalize by the denominator. Okay, now I look over here and I see, okay, I've got a square root of 5 on the top and a square root of 7 on the bottom. Those are not I can't reduce that at all. So here's what I'm going to do. This is when we use rationalizing the denominator. We cannot leave this radical in the denominator. So we are going to multiply the top and the bottom by whatever the radical is in the denominator. Now, why do we do that? Well, root 7 over root 7 is just 1, so we didn't actually change the value of this fraction. But then, whenever I multiply it by the root 7, that's going to give me those 2 7's under the radical, which means it's going to come out. So anytime you multiply a radical times itself, it gets rid of the radical because it's kind of like giving you that little pair of 7's, right? So now I'm going to just multiply across. So I have the 3 was on the outside, so it stays on the outside. I have the 5 and the 7 are going to go together on the inside. And then that root 7 times root 7 is going to give me 7. Now I just need to simplify what's in the radical. 3 root 35 over 7. Okay, now guys, I know that this is super tempting to be like, oh, 35 and 7, they reduce. No, 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 no. If something is on the inside of a radical, it cannot simplify with something on the outside. Things on the outside could simplify with things on the outside, or things underneath the radical, like we did over here. Underneath the radical can simplify with underneath the radical, but I cannot reduce something where part of it is under the radical and the other part is outside of the radical. This is my simplified answer. Now, sometimes you have to check that whenever you multiply these together, sometimes this will reduce, this radical on top, but we see it's a 5 and a 7, and those are both prime, and they don't have any common factors. Okay, our last example. So again, this is one of those ones where we're like, oh, 5 over 10, that can reduce to 1/2. No, 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 no. This 5 is on the outside, the root 10, that 10 is underneath the radical, so I'm going to have to rationalize this. So root 10 over root 10, so I get 5 root 10, and the purpose of multiplying it by itself is so that it will come out. Now again, I can't reduce these 10's, right, because this is on the inside and this is on the outside, but look, these are both on the outside and they can be reduced. 5 over 10 can reduce to 1 over 2, so this can simplify to the square root of 10 over 2. Okay, so I hope this was helpful review of simplifying radicals. Again, if you have questions over this, please talk to your teacher because we will use this all unit long.